SpreadSort is a sorting algorithm that aims to balance the performance characteristics of distribution-based sorting algorithms and the worst-case behaviors often seen in quicksort-like algorithms. It is designed to efficiently sort data with a wide range of values. Just like the folder there, the group of numbers are divided into bins or buckets. So the bins are like the folders, the pink, orange, and the blue-green folders. Spread sort is bucket sort applied recursively, where B equals n over C, where n is the amount of the numbers and C is the bucket size. While bucket sort might have a big bucket, solves this by sorting recursively for the bucket to have a maximum size, or else it uses intro sort if there is a bin beyond the size threshold. To make the bins uniform, it needs to find the minimum and the maximum value integer first before starting the main sorting.
SpreadSort has the time complexity of O of n log n, where n is the number of elements in the array. This is because the technique replicates the array O of log n times, and each copy takes O of n time to complete. SpreadSort has the time complexity comparable to merge sort, which is likewise O of n log n. SpreadSort, on the other hand, is typically to be more practical than merge sort because it does not require any more memory. Here is an example of SpreadSort's worst case, where the list is in reverse order. First, here's the breakdown of how SpreadSort works and its corresponding time complexity. First step is dividing the array into two, and this step has a corresponding time complexity of O of n. Secondly, the two subarrays will be sorted recursively, and this step's complexity is O of n log n. Lastly, the two sorted subarrays will be merged, and this step also has a complexity of O of n. With this, the overall time complexity of SpreadSort is O of n log n. Now, here's how the steps are applied to the worst-case scenario of SpreadSort. The array that contains 10 elements will be divided into two subarrays: 10, 9, 8, 7, 6, and 5, 4, 3, 2, 1. Following the division, the two subarrays will now be sorted recursively, as shown in the slide. Finally, after the subarrays are sorted, they will now be merged. And with this, the overall time complexity of SpreadSort's worst-case scenario is O of n log n. For the space complexity, SpreadSort is sitting at O of n, which uses space equal to the space occupied by the list.
So the pseudocode describes the spread sort algorithm. So a linear time sorting technique. So it begins by determining the range of values in the input array identified as mean and max value, and then creates a spread array here covering this range. Following that, it initializes right here a count array with zeros, sizing it according to the spread array. This count array is then used to track the occurrence here, to track the occurrence of each value in the input array. After counting the occurrence, the code updates the count array to store cumulative counts here. Subsequently, it creates an output array with the same size as the input array and places the elements in their correct order.
The provided code implements the SpreadSort algorithm. The roughLog2 function approximates the logarithm base 2 of a given input. It uses a loop to shift the bits of the input to the right until the result becomes 0, counting the number of iterations. The function is designed to handle both positive and negative inputs. The next function is called getMaxCount. It determines the maximum count for a bin in the SpreadSort algorithm. It calculates a logarithmic size for the input range and computes a relative width based on this size and a constant. The final result is a power of 2 constrained to be within the size limits of the data type. The third function is called findExtremes. It identifies the maximum and minimum values in an array of a given type. It iterates through the array, updating the maximum and minimum values as it encounters larger or smaller elements. The SpreadSort core function is a central component of the SpreadSort algorithm. It initiates the algorithm by finding the extremes of the input array, calculating a logarithmic range, and determining the number of bins. Memory is then allocated for the bins and their sizes are calculated. Positions within the bins are assigned and elements are swapped to sort the array within the bins. This function includes optimizations to avoid worst-case behavior and improve performance with real data. The SpreadSort bins function manages the sorting of individual bins. It iterates through each bin and checks the count of elements within the bin and decides whether to use a standard sorting logarithm, the std sort, or recursively call SpreadSort if the count is above a specified threshold. Once sorting is complete, memory allocated to the bin is freed. And the last function is called SpreadSort.rec. This function is a recursive implementation of the SpreadSort algorithm. It first checks if the count of element is less than 2. This is the base case scenario, in which case it returns. Otherwise, it calls SpreadSort code to perform the sorting and SpreadSort bins to handle the individual bins. This recursive approach allows for efficient sorting of subarrays. SpreadSort algorithm employs a combination of binning and recursion with careful consideration of performance optimizations to efficiently sort the arrays, especially when dealing with a broad range of input values.